I'm start recording and go for it.
All right. So I see some familiar faces, so that's great. Thank you for that. So my name's Joan Horvath. Everything I do is joint with somebody named Rich Cameron, who is sick as a dog today, poor soul. And so I am going to be doing this alone. It's a little bit of a multimedia extravaganza here, so bear with me. So some of this was supported by the grant that you can see there. Just we always like to mention that. So our story is a little bit, our background is a little bit important for what we do, and I'll get into that in a minute. But basically, I like to say I'm a recovering rocket scientist. I'm an MIT alum, so shout out to the other MIT folks here in aeronautics and astronautics. And my partner, Rich, developed some of the earliest consumer 3D printers. So we came into this as we were both in a 3D printer company. There's Rich showing two of the printers that he designed, one of the earliest RepRap printers and the Bakito, which was a commercial printer. So the two of us were 2/3 of a 3D printer company. That company got its Kickstarter design copied by a Chinese company, and they started to make the printers for less than our cost of parts. So that was the end of that. So in 2015, we said, what could we do that nobody knows? Nobody could kind of upend us that way again. And we said, well, nobody's doing training, teaching people to use 3D printers. So we started the company Nonscriptum as a 3D printer training company. And then most of the people hired us for schools, and it turned out that nobody knew what to do with a 3D printer, which is still somewhat true. So we started developing curriculum. And so we'll talk about that curriculum now and make our most recent 3 books from Make, which are using 3D prints and other things to teach math. So our philosophy in developing our math curriculum is that to teach geometry and intuition first, and then algebra second. And so when you do that, you can teach a lot more sophisticated math a lot younger than you might be able to otherwise. And we try to practice universal design, which is the premise that we make something accessible for those with disabilities, particularly visually impaired. A lot of our stuff was done originally for visually impaired students, actually, which was that grant. It can often make it better for everyone. So we develop our models in a program called OpenSCAD. It's a free open source constructive geometry program. Using OpenSCAD automatically teaches you some geometry, which is very powerful. And it's, I'll show a screenshot of it in a minute, but basically you code models in a programming language that's kind of in the C, Java, Python family. And it has 3D geometrical primitives, so you can do this fairly naturally. And if you want to download it, it's at openscad.org for Mac, Windows, and Linux. There are block versions of it, but they're subsets, and our stuff won't work with that. And oops, it says second hour because this is from a teacher training. Sorry, oops. So this is what OpenSCAD looks like. It allows you to program things like a rectangular solid, which it calls the cube. That's a cube that's 10 millimeters by 20 by 30. And then you can do fundamental geometrical transformations on it, like translate. So you see here a cube and a sphere that's been moved, and you can build up pretty nice stuff out of that. And OpenSCAD, interestingly, is the only command line interface accessible CAD program. So if you're blind, you can, in fact, use OpenSCAD. And so some of our premise was, could blind people also at least alter and use these CAD models, and people have been doing that. It's been really interesting to see that evolve and see that workflow evolve. And if anybody's interested in that aspect, I can talk to you offline. And so the question came up is, can we teach everybody STEM a little differently this way? So we started off with science projects. So here are some examples. These are from our 3D printed science projects books. This is a model of plant growth in OpenSCAD. The camellia there and the aloe are the same model as each other, with just some parameters changed, because we realized that, as we heard in the last talk about math models, it's not easy to develop a math model. So what we've done is develop a model with a lot of parameters so that a student or a teacher can go in and change parameters. They don't have to develop a model from scratch, but they can change parameters and learn some fundamentals from that. We also built models of World War II airfoils. So these are accurate World War II wings of various sorts. You put them on a postal scale and you blow a fan on them. When you blow a fan on them, they generate lift, they become lighter. And you can tilt what their angle of attack is and all that kind of stuff. So these will print on a pretty small, on a Prusa Mini to talk about a modern machine. And they're printed in 3 pieces. And so you can build yourself a whole Air Force, and we've had some really wonderful aeronautics classes with 11 and 12-year-olds at varying levels of sophistication with these. So that was all good. And then people said, well, wait a minute, could you use universal design to do a whole math subject with 3D printable models and also some other hands-on activities? And so out of that, came Make Geometry first, and then Calculus, which has been by far the most popular book, interestingly. And then Make Trig, which came out a couple months ago. And so what I'm going to do is show you a few slides of that and then show you some of the actual models. So for instance, this is from Geometry. This was originally designed for blind students. So it is a positive model of a cone, a half sphere, and a cylinder. And negative models, these fit, the blue ones fit into their corresponding green ones. And so what you can do is you can fill the cone, the half sphere, and the cylinder, and you can discover that two of these fills one of these, and this plus this together gives you that. And so you can experiment with that. And the fact that you have the positives lets both blind students and sighted students feel what this feels like, but you can put them together to prove to yourself that the volumes are the same. So it's been a really fun tactile thing. And also, you can also win money in bars this way because nobody has good intuition for volume, and you can really, especially with a bunch of techies, it's fun. We've also, you probably made sine waves with a toilet paper tube at some point. What you can do with the models instead is we've created models where we are plotting the unit circle here. So this is, let's see, sine 2x. So we've plotted in the vertical direction, sine or cosine, as we go around the unit circle. And then you can take that and roll it out on Play-Doh, and you can get your sine waves, and you can make them. The model is designed so you can make various levels of these. Now I'm going to stop sharing my screen and show you some models in real time here, which I think will be funner. So if you wouldn't mind spotlighting me here, so I'm a little bit bigger. I don't think I'm spotlit yet. So just mouse over my square, and then click on those 3 little dots, and you should be able to spotlight for everybody. Or you can make me co-host, and I can do it as you prefer. Let's see, I'm not able to do that. Well, what people can do is you can click on the 3 little dots yourself and click on pin. And that will make me bigger for you. If for some reason that it's not possible to do that. Okay. Anyway, all right, being that as it may be. So go ahead and pin me so you can see me. So here is, you have probably seen a model like this, made out of paper, right, to make a cube. And so the insight we had, starting with the point of blind students, was that what would happen if you completely filled this volume instead, so that you could fold it up and make your cube. But instead of fussing around with trying to tape things together and all the pain and agony that goes with that, this is now filled. This was printed in a flexible material because we do a lot of shows, and the stiff stuff only will last 1 kid, but this will last forever. So the OpenSCAD model is only like 5 or 6 lines long. It's quite short, actually. And what you can do is hand this to a blind kid and say, okay, what's the volume of a pyramid? And they can reason that, because they can say, oh, it's 1/6 of a cube, and how does that work? And then they can think that through. And so it's a very powerful way of doing it. And the OpenSCAD model has number of sides as a parameter. So here is instead is a 12-sided dodecahedron. And if you've ever made one of these out of paper, you know it's sheer agony, but you know, do it this way is much faster. And also you can sit there and say, well, wait a minute, these completely fill it. So what is the volume of each of these pyramids and what's the volume of a dodecahedron? And you can get there quite quickly. And you know, all you really need to know is the length of the side. And so, you know, you don't have to print them on this kind of material. You can also print them on fabric. We've done that too. So you get the idea there. So one of the other things we've done is to bring a little engineering into it is we've made models of arches. So this is from our geometry book. So these are all independent pieces put together with a little bit of museum tack. And if you're an ancient Roman, you have a circle centered here. You build out your circular arch, and it's pretty strong. So I can lean on this, but you can see it's starting to fail here and here because the force is being transmitted sideways, and there's nothing really to stop it. But if you were a smarter medieval person, you still have circular arches. You still have a circle to work with because all you had was a rope to work with. I have another circle here, and now I have one different piece here, the keystone, and I can lean on that as hard as I want and nothing will happen. And so you can talk about that. These are models from the geometry book. And then we continue on to show that if you repeat that pattern, it is fantastically strong in this dimension, quite weak in this one. And so these are from our Make Geometry book. The project we use throughout Make Geometry is a castle. So this is an OpenSCAD castle, and we scaffold throughout, adding things to the castle. You can also teach coding because OpenSCAD is coding, so you can learn loops and rotation and translation, and you can imagine how you can sort of build up a pretty nice math curriculum around this, you know, by the time you're done. And also, of course, our good medieval Gothic arches here and how to generate those. And so we found this to be a really good model. We teach in a gifted program after school, so we have a little bit more flexibility. But a castle is a really nice low floor, high ceiling kind of activity to do because you can do all kinds of stuff, right? And just keep building onto it. And I can show you some examples there if you want. Here's a probability model that I'm very fond of. So if I have one 6-sided die, I have an even probability of 1 through 6, right? If, however, I have 2 dice, there's no longer a way to get 1 anymore, but there's a whole bunch of ways to get 7. 3, 4, and 5 give me different distributions. So if I have 6 coins or one 12-sided die, I end up with different distributions of 1 through 12. And so it's a fun way of thinking about that. And if you really want to motivate kids, you can talk about how they can design their sword of whatever, depending on whether they want to have a 12-sided die or 2 6s or what have you. And then calculus in 1 minute with the time I have left. So here's how we do Make Calculus. So if you haven't had calculus, don't turn off the screen. It's okay. That's the idea, is to teach us. So our motivation was to see if you could, how young could you teach calculus concepts? Because calculus is where math starts to be fun, right? A lot of elementary math is kind of boring. So the question is, how could you teach calculus without any algebra at all? And that was where we started. And we have evolved from that a little bit. Okay, so here I have Lego bricks. And I have graphed with Lego 0, 1, 4, 9, 16, right? X squared, 0, 1, 4, 9, 16. And I asked the question, well, calculus is all about how things change, right? So what's the difference between these two? The difference between 9 and 16 is 7. So I'm going to take a 7 here and I'm going to add that. And then the difference between these two is 5. I'm going to add that. The difference between these two is 3. I'm going to add that. The difference between 0 and 1 is 1. And so my curve of differences, which has the calculus fancy name derivative, is the curve 2x. And so I have just taken a derivative with Legos. And then if you've taken calculus, you say, well, what's the area under this curve? The area under this curve should give me my original curve back, otherwise known as integrating. So from 0 to 1, that works. I get that. Add the first two, I get 4. I add the next ones, I get 9. I add the next one, whoops. I get back to my 16. So if I add, I can differentiate and integrate with Legos. And then you say, well, what happens when you want to do something continuous? So what we've done is develop 3D printed models that are scaled to Legos. And so I can talk about my x squared curve, and I can talk about its derivative, which is 2x. And I can talk about how I can move between these two. So we have an OpenSCAD model that you can put in an equation for the derivative or the integral, and then it'll make these two right-angled models. And so what gets to be really, really fun is where'd it go? Hang on one second. Forgot to bring my good one. All right. So for circular functions, what's really fun is here I have a sine wave. Its derivative is cosine. Whose derivative is minus sine, whose derivative is minus cosine, and I go the other way to integrate. So you can talk about the circular functions with these models. And something that's really, really nice to do is talk about surfaces of revolution, which are very hard to do. So we have an OpenSCAD program where you define a 2D shape of some sort, and then you tell it which axis to rotate it around. So if you rotate that around, then you can see that when I take my square and I rotate it around the corner, I will get this. If I were to rotate it about the center here, I would instead get a cylinder. And so you can really do a lot of stuff with these models. So that's the kind of stuff we've been doing. So let me go back to sharing my screen here. Oops. So another thing that we have available now as of yesterday is a LinkedIn learning course. If what used to be lynda.com. So if your school or your library has a subscription, Assembling Calculus is out there now, and it walks through some of these models. But if not, here are our books. And as a special gift, Make has given a discount on all books and magazines in the Maker Shed until Valentine's Day as a special Valentine to this group. With that code. So if you want to buy our books or anybody else's books for that matter, but ours are cool. I'm kidding. You can go ahead and do that. So you can take a screenshot of that. And our LinkedIn learning courses and our books and all that stuff are on our website, which is nonscriptum.com, which is our creative partnership. So if all that went by quickly and you want to look stuff up, we have a lot of stuff on Nonscriptum, including links to all our models. All the models you've seen are open source. So we have a link to GitHub repositories on the front page of nonscriptum.com. So if you go ahead and go to nonscriptum.com, scroll down the bottom, you'll see GitHub repositories for each of our books. We'd like you to buy our books, of course, but failing that, the models are there and we like comments. All right, so go ahead and grab a screenshot of that and I'll give you a second. I see there's all kinds of stuff in the chat. So let me stop sharing here. And I'll take questions. I know that was a high-speed walkthrough, but in 20 minutes, what can you do?
You actually have a few minutes, so feel free to any questions.
So I know some of you are doing math stuff. So Stephen, I was in your talk. So if maybe some of these could be exemplars for teachers, because it's it's an interesting problem, initially we said, well, we'll teach people how to create models, but they just don't have time. And I've discovered that it is a very powerful thing. For those of you who weren't in Stephen's talk, and some of your grad students are here, I guess. Those of you who weren't there, he was talking about teaching people by having them do models, and I applaud you because it's hard. We're fairly sophisticated people in this stuff, and we have to work hard to do this.
Yours are the coolest. I'm looking at the ones on my shelf. They don't do that kind of stuff. Those are great. What's it like when you and your collaborators sit down to come up with an idea, like the spinny cosine thing?
Well, what the calculus book actually partly came out of the fact that Rich is self-taught. He's a pure hacker. Had a very bad experience in high school, and which we could talk about online at some point, because he thinks very differently. And so at some point he said, in our partnership, he said, I'd like to learn calculus. And I said, okay. So I started talking to him, and eventually he said, I don't like any of this algebra stuff. And so I handed him Principia, Newton's Principia, which Principia has no equations in it at all. The original book describing it's all diagrams. And he said, oh, well, this is obvious. This is good. And he said, wait, I have to build myself a model. And they kept saying, wait a minute, I have to build myself a model. Principia, Principia Mathematica, if I could spell it, Mathematica, and it's by Newton in 1666. That's not a typo. So that's the original calculus book. So the original, yeah, okay, there you go. Thank you. So the original calculus book has no equations in it. So Leibniz came along later and changed things. But basically then he said, well, I need to make a model. And I said, this is a thing. And, and then it took a fair amount of back and forth on figuring this out. On the other models, usually we just sit down and argue about it. I'm a very traditionally trained engineer, and we say, let's come up with a model for this or that. And then, he'll go off and think about it. And we just, we think very, very differently from each other. And so we just sort of fight about it for a while. And these things come out. But he's a very gifted geometric person. So I'm privileged to be half of that.
Makes sense why he struggled in school with that kind of disposition. He's going to read the Principia instead.
Yeah, well, and it's unfortunate. So all those of you who are teachers, if you have somebody who doesn't show their work and just comes up with an answer, they're not necessarily cheating. Because that was his problem, is he just could look at something and say, well, the answer is this. And, that didn't play out well in Los Angeles public school, unfortunately. But he's making up for it now, I hope. But have any of you used our books in the classroom? They're out there enough that we're starting to see them in the wild a little bit. No, not yet. Okay, well, cool. And I'm happy to collaborate with people and chat with them. I'll put my email in the chat. Can I spell my own website? Probably not.
Are you considering translations?
Excuse me?
Are you considering translating the books?
There was some interest that would go through O'Reilly, the publisher. So Make is an imprint of O'Reilly, sort of, at this point. And so O'Reilly handles things like translations. But you can drop me a line and I can put that through. Usually the translation is initiated by a foreign publisher, is how that works in publishing these days. And so a foreign publisher will usually come along and say, I want to, insert language here, version. But sure, we'd love to have them published elsewhere.
I'm not the publisher, but I can see a lot of people that would be very interested, but the language barrier might, the technical language, etc. Just an idea, or a hopeful idea.
Yeah, I think they were interested in some of the Asian languages. That's the only ones I know of that there was some discussion, that they're interested in some of those. But I don't think there was any. I'm not aware of any increase in any European languages at this point. But the idea is to make them universal. So what happens when we do a lot of maker fairs and things like that. And so what happens is we put out all these models on a table and kids go completely bonkers. You know, my very favorite moment in all this, and I know we're gonna get closed in a minute. My very favorite moment in all this was this little girl came up and she was wearing a fairy princess outfit at Maker Faire Bay Area, I think. And she played with all our puzzles, and we have tons of puzzles. I'm just showing you a tiny subset of what we have. And so we have all this stuff out there. And her mom finally said, you know, look, we got to go. And she was dragged off, shrieking at the top of her lungs, no, more math, no, more math. And we high-fived each other because that's what you want, right? Kids shrieking at the top of their lungs, no more math, especially a little girl in a princess outfit. So it's like, that's my success moment, you know, that we put up with all the other stuff, is when little kids complain that they want more math. So we have taught the calculus stuff to actual children, gifted kids. And the youngest one was 9. And he had not had Algebra 1 yet. And his mom was dubious, but his parents are both scientists. And he was able to talk about what an integral and derivative was and do things with Legos and all this kind of stuff. So he couldn't do algebra, but he could do that. So teach calculus to little kids. That's my closing message. Because then they'll learn all kinds of cool stuff.
Thank you. Outstanding project.
Thank
Good
you.
work.
Thanks, Joan.
Thank you.